Hello, my name is Sungko Kim. Today, I'll present our paper, Memory-Efficient Fixed-Point Computation. Our work attempts to decrease the memory footprint of fixed-point engine and abstract interpretation without sacrificing its precision. Abstract interpretation is a general framework for expressing static analysis. An abstract interpreter will take a program as an input and generate its invariants as an output. These invariants are then passed to client applications that perform either bug finding, verification, or optimization. Program abstraction is the first step. It generates an equation system from the input program. This step is parameterized by an abstract domain whose values express the program invariants. The next step is the fixed-point computation, which solves the equation system. The solution of the equation system will be the invariance of the input program. This is an example abstract domain that captures a lower bound and an upper bound of some variable. Once the abstract domain is chosen, we can extract the equations by abstracting the semantics of the program. Assuming a program in the form of control flow graph, we can assign program points pre and post for each basic block. An invariant at a pre will be the joint value of the invariants at post of its predecessors. And an invariant at post will be the invariant of the corresponding pre applied with the abstract transformer. Fixed-point computation solves the equation system by first initializing the abstract values and updating them until there is no change. The final fixed point is the program invariance. Here, note that the abstract values are kept for all program points during the fixed-point computation. Finally, the computed fixed point, or the invariance, can be used for client applications. For example, invariance at pre3 can be used to verify the user-provided assertion in the input program. Now, this step of generating invariance can take a lot of memory because real-world programs have a lot of program points and each abstract value can take a non-trivial amount of memory. For example, to analyze the following two Linux device driver benchmarks, NASA's open-source static analyzer required 46 GB to analyze the first and spaced out at 64 GB while analyzing the second. Using our approach, we could reduce the first to 56 MB and make the second to complete using 21 GB. To lower this cost, many improvements have been made on the abstract domain part. However, this is inherently domain-specific. Therefore, we focus on the domain-agnostic part, which is the fixed-point computation. To restate our goal, we aim to improve the memory efficiency of fixed-point computation that uses Berdan's recursive iteration strategy without sacrificing the precision of the output invariance. An iteration strategy determines the order in which the abstract values are updated during the fixed-point computation. And recursive iteration strategy is a commonly used strategy adopted in tools such as the following. Recursive iteration strategy is based on the loop nesting structure of the control flow graph. For this goal, we present a deallocation strategy that is optimal for the recursive iteration strategy. Our first key idea is to perform the client application during the fixed-point computation. This provides opportunities to deallocate the abstract values earlier. So originally, these two were separate steps and the invariant table in the middle were taking up a lot of space. Now, we interleave the fixed-point computation and the client application so that the invariant table is no longer needed. Our second idea is then to analyze the structure of the control flow graph to determine the best points to use and deallocate the abstract values. Recursive iteration strategy itself is guided by the CFG structure, so we can have decent memory optimization technique by looking at this structure. In particular, we focus on the nesting relationship between the loops. Now we will look at an overview using 3 examples. We begin with a cyclic graph that has a user-provided assertion at the basic block 3. Recursive iteration strategy for this graph is summarized as its topological ordering. When a node is visited in this ordering, its pre-value is updated and then its post-value is updated. Here, you see the whole trace of the execution of the fixed point engine. In the existing approach, the evaluation of the assertion checks and the deallocation of the abstract values are performed after the fixed point computation is finished. In our approach, we interleave them with the fixed point computation. To give you an example for determining the deallocation point for post value, consider post 2. It has successors 3 and 5, and 3 is visited later than 5. Therefore, update pre-3 is where the post 2 is last used. And our approach can deallocate post 2 after that instruction. For determining the evaluation point for assertion checks, consider the assertion check at 3. Pre-3 is used to evaluate the assertion. Because this instruction is where pre-3 is last updated, assertion check at 3 can be evaluated after the instruction. Because this instruction has been hoisted, the deallocation can also be hoisted. Because there are no assertion checks for the rest of the basic blocks, the allocation of pre's can be hoisted as well. Now, adding this edge introduces a loop in the graph. Recursive iteration strategy is modified to reflect this change. Nodes grouped by the matching parentheses represent a loop in the graph. With this change, the loop elements are iterated until the values for them stabilize. In the example, the trace for the loop element 3, 4 is repeated until the loop stabilizes. Because we cannot predetermine how many times the engine will iterate over the loop, we must check the stabilization in each iteration. In the existing approach, evaluation of assertion checks and the deallocation are performed at the end. With this change, the allocation of post 2 can no longer be performed after the update of pre-3. We cannot know how many times pre-3 will be updated. Therefore, we must wait until the loop 3-4 stabilizes. Similarly, the allocation of post 5 and post 6 must be delayed until the stabilization. Things are similar for the evaluation of assertion checks. If we evaluate the assertion check after the initial update of pre-3, the result might not be sound because of the subsequent updates. Therefore, it must be evaluated after the loop stabilization. Consequently, the deallocation of pre-3 must also be delayed until the check is evaluated. Pre-3 can also be deallocated in the beginning of each loop iteration. This is because pre-3 will be reset during the loop iteration. While this example only shows the resets for pre-values during the loop iteration, our approach resets post-values that are generated in the loop iteration as well. Adding this edge creates our final example with nested loops. Recursive iteration strategy is again modified to reflect this change. It clearly shows the nesting of the loops. The execution trace now has repetitions for the outer loop elements. The outer loop is iterated until it stabilizes. Note that inner loop is iterated until its stabilization in each of the outer loop iteration. With this change, the allocation of post 6 can no longer be performed after the stabilization of the inner loop. We cannot know how many times pre-4 will be updated. Therefore, we must wait until the outer loop stabilizes. This is in contrast with the allocation of post 5, since post 5 can be deallocated after the stabilization of the inner loop 3-4. This is because post 5 is generated in each iteration over the outer loop. The difference comes from the fact that node 5 is contained in the outer loop, while node 6 isn't. Now the evaluation points for the assertion checks must change as well. It should wait until the stabilization of the outer loop. Consequently, the deallocation of pre-3 must be delayed as well. Like how the allocation of pre-3 happened at the beginning of each inner loop iteration, the deallocation also happens at the beginning of each outer loop iteration. Now we summarize our algorithm. To determine the deallocation point for post v For all successors S of V, we find the header of the maximal SEC that contains S but not V. The allocation of post V is done at the rightmost of these headers according to a new total order that we define. Also, to determine the evaluation point of assertion for V, we find the maximal SEC that contains V. More details are in the paper. Theoretical results for our work is as follows. First, for the recursive iteration strategy, our technique identifies optimal evaluation points for assertions and the allocation points for abstract values. To prove this, we formalize the notion of fixed point machine in our paper. Next, the invariants computed by our approach are the same as the existing approach. And finally, optimal evaluation points and the allocation points are found in almost linear time. This has the same time complexity as computing the recursive iteration strategy itself. For empirical evaluation, we have implemented our approach in a tool called MyCos, which extends NASA's ICOS. This supports all abstract domain that ICOS supports and supports interprocedural analysis. We evaluated our tool on two tasks. The first task was verifying user-provided assertions. It was performed on 784 SVComp benchmarks, and we used reduced product domain of zone and congruence. The second task was proving absence of buffer overflows. It was performed on 426 Arch Linux core packages. An interval domain was used in the task because the benchmarks could not finish within the time limit with the previous domain. The scatter plot shows the results for memory performance for task 1. The y-axis shows the memory footprint of MyCos, and the x-axis shows the memory footprint of ICOS. The red crosses are the benchmarks that timed out or spaced out in ICOS. They all completed in MyCos. Benchmarks below y equals x line implied that MyCos required less memory footprint than ICOS. All benchmarks required less memory in MyCos. We measured memory improvement as memory footprint of ICOS divided by the memory footprint of MyCos. Higher is better. The minimum improvement was 1.11x and the maximum was 1000x. The geometric mean of the improvement was 25x. The memory improvement was greater on programs for which MyCos required larger memory footprint. This trend is shown in the scatter plot. This trend can also be seen in this histogram. This histogram shows the memory improvements for benchmarks for which ICOS took more than 9,865 megabytes. This is the fourth quartile in terms of the memory footprint in ICOS. The x-axis shows the memory improvement, and the y-axis shows the number of benchmarks for the memory improvement. The average memory improvement for these benchmarks were 108x. This is a drastic increase from the 25x, which is the total average. This table shows 5 benchmarks with the best memory improvements for task 1. The first 2 columns show the time and memory footprint required in ICOS for these benchmarks. The next 2 columns show the time and memory footprint required in MyCos. The last column shows the memory improvement. This scatter plot shows the results for the time performance for task 1. The y-axis shows the runtime of MyCos, and the x-axis shows the runtime of ICOS. Benchmarks below y equals x line imply that the ICOS required less runtime than ICOS. MyCos was faster than ICOS in most of the benchmarks. The geometric mean of the speed of MyCos was 1.3x. Essentially, there was no loss in time efficiency. Now this shows the memory performance result for task 2. Here also, all benchmarks were below the y equals x line. The minimum improvement in memory was 1x and the maximum was 45x. The geometric mean was 2.3x. This table shows 5 benchmarks with the best memory improvements for task 2. Again, The first two columns show the time and memory footprint required in ICOS for these benchmarks. And the next two columns show the time and memory footprint required in MyCOS. The last column shows the memory improvement. This shows the runtime performance result for task 2. For task 2, the geometric mean of speedup was 1.08x. Again, there was essentially no loss in time efficiency. To summarize, our approach interleaved the fixed-point computation and the assertion checks for earlier deallocation of abstract values. Our approach identified the optimal assertion check points and deallocation points for recursive iteration strategy. We have an almost linear time algorithm to compute these points. Our code is available on GitHub.